What are you talking here? Okay, recording. In the last class, actually, we missed here. So it was the soil uh, property. The property, it was plain strain. It is actually axisymmetric condition. Okay. So what is axisymmetric condition? What is plane strain? I think you know. You know what is plane strain and what is axisymmetric condition or plane stress condition. Okay, I'll explain a bit. Plane strain condition. So usually, I mean, uh, in 2D, in Parliament 2D, Parliament 3D, say 2D analysis, so whatever it is, analysis has, I mean, two parts. One is plane strain condition. Okay. Then other is plane stress condition. Now, what is plane strain? Plane strain, say you have an embankment or say a retaining wall, a retaining wall, say 500-meter and so on. So this retaining wall, okay, it has, I mean, in this direction, we can say epsilon y, say here epsilon y is the same at any point. Okay, so in this case, we can go for plane strain condition. And then plane stress, plane stress is very thin. Okay, then here the stress, here the stress the same. Okay, sigma y same. So this is plane stress condition. Okay, so in 3D, so in and then axisymmetric condition, as I explained, it will be circular like this, cylindrical coordinates like this. Okay, so when you, I mean, go for 2D analysis, we must select either plane strain or plane stress. But here maybe it doesn't have plane stress. I have to check. But in my FEM program, I have this plane stress condition, also axisymmetric condition. I have my own, I mean, pattern method, I mean, program. You can check here. Okay, model, axisymmetric, no, only plane strain and plane stress. Sorry, plane strain and axisymmetric condition. Okay. So whenever you, I mean, do 2D analysis, you must consider, I mean, this thing, whether your condition is axisymmetric, I'm sorry, plane strain or plane stress. Axisymmetric actually is a 3D, in fact, it's 3D, 3D, but you can do by 2D analysis. B matrix is 4 by 4. I mean, B matrix is 4 by 4 like this. So in that program, then now we can see if you go there. After that, I calculated that one, and here is the result. Deformation 0.5 we applied here. Deformation 0.5, you see, we applied here. So now this chart I already made. So this is the chart. So x-axis is sorry, y-axis is fy. How I calculated this? Okay, I can go again, or we can I mean make one, again another one. Say project node number, you have to fix it first. I mean after selecting mesh and after I mean mesh generation, then y because it has x direction, y direction, so it is uy. As I applied the negative, and also the force is negative. The force is negative, so it is invert sign. You'll get this one. Then you can change this one, everything. Just right click setting, you can change the name and so on. Okay, say here the chart name is node 4. So here the chart name, so FY, YX, just say you. I mean, U displacement, say settlement, settlement. Then you can change it this way. It is in millimeters, it is in meter, and so on. Then Fy, you can per radian. You see it's per radian. Fy per radian. Okay. So you can change in this way. Okay. So you see this is settlement, and this is Fy. And then you click it here. Then also you can change the chart. I mean this one, double click, not double click. It's, okay, here note 4, or you can say load displacement curve. Load displacement curve. Displacement curve. You can change here. Apply. So this load displacement curve, and so on. You can copy it. Copy. Control C. Then you can paste in the Word file, and so on. And the maximum value, corresponding value you will get from here also. There's a table for different, I mean, steps are different UI. So it's for 50 milli, it's meter, 10 minus 3, that is 0.05 milli. So we have 93.694. So if you multiply this one is 2 pi, so it is 588, like this. So you can copy it and then you can paste. Okay. So I'm closing this one. Okay, yeah. Okay, say, because it was our previous I mean lecture. And also flexible foundation. In flexible foundation, as I messed with that plane strain and axisymmetric condition, so there was problem. There was problem. Now, okay. Now in okay, I mean flexible foundation, if you see, so we applied the load. I mean the stress here. We applied this one. Here this application line load we applied, and here we have, I mean mat. This plate element that is the raft or mat or say footing. We applied minus at 188. Minus 188. It comes if you divide that. I mean total. I mean total load, that is 93 into 2 also, or I mean 588, then divide by 5, then we get this one. So you apply here, then you can see the stress, okay, so not deformation, whether it is close to 5 or not. Close to 5 or not, 0.05 million or not. So you see, I mean the deformation is 0.04953. So very close to 5. Okay, it means that your, I mean, deformation or your calculation is correct one. Then you see the deformation, total deformation of the deformation. So, okay. You can copy and you can paste it. You can copy and then paste in your Word file. Okay. So this is the system that you can use in your Plaxis. Okay. For your case, I mean this FYDP case, we need, okay, we need only 3D, 3D, FPM 3D, I mean Plaxis 3D. So today I'll talk on Plaxis 3D. Don't say, Don't say. So 3D. So before that, I mean, I need some explanation here. So what we used in 2D, we used plate contain condition sand, sand. Okay. For sand, we use drain condition. Always, I mean, sand is drain condition except earthquake analysis. Earthquake means, I mean, during earthquake, only that, I mean, some seconds, drain. And then clay type soil and clay soil. Clay soil, it has, okay, undrained condition, undrained. So here there are 3 types of undrained, okay, in Plaxis. 3 types of undrained, which one you will use? Okay, I will explain here. So in your material model, okay, and there are three types on undrained A, undrained B, undrained C. Undrained A, undrained B, undrained C. So if you go down, so you'll see the for molecular model, okay, undrained, drain, it is drain, undrained A, undrained B, undrained C, non-porous. It's there, So undrained A. So whether we will use undrained A, undrained B, undrained C, depends. So undrained A parameters is undrained A parameters. Undrained A parameters is say phi dash. Parameters undrained A phi dash and say I mean C dash or CU dash C dash. These things you need. Okay, this one it's very difficult to get this on back. So what we can get we get directly CU. If it is CU, okay, if it is CU, if it is CU, I mean CU dash. So this is D, and then B. Sorry, and then B. If you have CU, that is pi equal to 0, pi equal to 0. So I mean you can use quickly and then B. Okay. So the molecular model support and then B. Okay. Also C supports and then C also. So hardening soil model, soil model with small strain stiffness also and then B is supported. Okay. So this this model we actually will use for our case. But it's better use this hardening soil model for sophisticated analysis. Okay. So I will delete this one. Now, we'll go to the 3D. We'll go to 3D. Okay, keep it open. Now 3D, exactly the same. If you know 2D, then it's very easy for you to, I mean, uh, to use 3D Plaxis. Very easy. It's exactly same, almost same. So we'll open this. We'll open 3D Plaxis Connect version 8. This is V21. No, not this. 2D 4010. What is 3D? That's LE. Okay, 3D Connect version. Oh, no. This is 3D Connect. No, exit. 2D. What is that? 3D. 2D. 3D Connect version. Okay, 3D input. Okay, this one. So this is 3D Ultimate. Continue. Start a new project. So you can write the bearing capacity of pipe. Initially, we'll calculate the bearing capacity of pipe. Bearing capacity. Okay, of pipe. Okay, model. Now it's full. You see there is nothing because it's 3D. And there is 10 node, only 10 node. Okay. So 10 nodal element in 2D. And here, the unit is length, meter, kilonewton, day, and so on. If you see water table, it's 10, 10 to the power. You can also, make it 9.81. Or we'll keep it like this. Okay. Now we'll, the same as previous, yes, last class, we have to create borehole. So borehole, just click it, this toolbar, click borehole, and put it here, somewhere here. Okay. So now say it is 0, x is 0, y is 0. Okay, y is 0. Water table is at the 0. Now we'll use negative for downward direction. So add layer, say -30. You can use positive also, no, -30 top to that. So we don't have any soil here. If you go down there, there is no soil now. There is no soil. So come here, material. So as I have many material, I can get it from here also, source. It is clay, it is sand, and so on. No need, actually, it is sand or say one, it is sand one, or whatever two. So bring it here, and clay also we can, it's a hardening soil parameter, in fact, it is. Yeah. So hide it. You can save these things. Whenever you need, you can change. Now we'll change this, modify, edit, or double click it, then you can say this is more column clay, more column clay. If it is more column model, then it is hardening soil model, you see. So it's more column model. Okay, the material is not valid. Yes, it will not be validated because they're different model, different models. So these are the parameters we have. So mechanical, so you see there is no parameters here. Okay, this is okay. So invalid. Now we can E, say E is 30,000. Say 30,000, and it will come from your, oh no, it's material model B. Yes, B is given. Then Poisson's ratio, say for clay step solid is 4. You have to use your own. You'll come here. So you see these parameters, you don't need anything, only SU or CU, that is the state is given 50. Okay, it's 50. So your case is for this 60 or 50, whatever you like. So your parameter. This is one, and then this is MK. And then now I will edit the stand. Okay, the stand. Then more column stand. More column stand model. Here, more column model. Again, it will show this thing. So we have these parameters. Mechanical model, you already know this, and that's why I'm going very fast. So this is 40,000 kPa. As you know, ratio, and here you see drain model, drain, because sand is drain and clay is, you see here, sand is always drain, and clay is undrained, undrained, but undrained A, B, C, but we'll use undrained B, undrained B. Okay, 43, the Poisson's ratio for sand, say 0.3, or 0.25, whatever you like. Okay, because this is arbitrary. So C is 0.1, you would have say pure sand, There is 31 degree, phi, and psi is 1. As we said last class, psi is equal to phi minus 1. Phi minus, 30 degree, phi minus 30 degree. So it is, 1. Okay. So, okay. Now, I guess the bottom, say we have two layers there, two layers. So the top layer is say 5 meter. Okay, 5 meter, that is clay. That is clay. MC clay. Then add again layer, one layer, say there is up to minus 30 meter. So this is sand. Then okay, so you see there are two layers. The top layer, it is MC clay layer. Then bottom layer is, bottom layer is sand layer. Okay. As we have, we'll have piles, so it's better we structure, we change, this one, whether the interface, interface is 0.67 is good, 0.67 is derived, 0.67, and then and also interface is 0.7. Okay, it's derived, when it's automatically come. Oh no, it's main one. Sorry, main one. So 0.7. Okay, we'll keep in this way. Soil structure interaction, because there will be sand inside, solid material is concrete material inside this one, because we are going to get the bearing capacity of pile. Okay. Now we have created the soil. This soil, you can change this color also. You can change. Say here, MC clay color is not good. Go here, edit this color. Okay. You better go, use different color. Different color. Okay. Okay, this is, I mean, clear as then, huh? Now, okay, and then we did not give that one, sorry. Soil, huh? Soil, we did not modify this layer. No, not modify this. You cannot do it. You have to do it. I mean, project properties. You can change this model, huh? So it was by default, it was like this. Say 20 meter by 20 meter, x 20 meter, and y also 20 meter, huh? 20 meter. Okay, you can change anytime, huh? Anytime. Okay, it's 20 meter by 20 meter and 30 meter. I mean the depth. Now, we'll insert, I mean, pile, huh? We'll insert pile. So here, just follow this, I mean, toolbox, create line, this line, huh? Create line, there the top, anywhere you can put it, you can just come here. Okay, say 20 meter pile, huh? Or 15 meter, or 20 meter pile. Okay, now you can enter, and now you can change it, huh? So say at the, I mean, center, 10 by 10, x10, y10. Okay, at the center, x10, y10, and it's 0. I mean, 0 is top level. Then bottom also 10, because it will be a vertical one. Y will be, x will be, y will be also 10, vertical one. Then z will be, say, 20 meter pi, minus 20 meter. Okay, 20 meters. So this is your line. This is line. It's still, it doesn't do anything. So there is a line here. If you go there, geometry, then you will see there is a line. You can change from here also, the which one you use, but or just right click this line, right click. It is right click this line, create. Now create what we want to create. We want to create embedded beam, that is pile. Okay, not create beam. Beam is above the surface or above the ground, which will act as a big column also. And then below the ground, it is embedded beam. Okay, below the embedded beam. Okay, so now it is, this line has embedded beam. You see this embedded beam. Okay, but it doesn't have any material. You see, material is nothing, no material. Okay, none. Because we did not define the material. Now, go here, click here, embedded beam. You don't have anything, but I have here. I can directly get it from there. Or, okay, the Plaxis parameter, I'll give it to you. This one is better. Say, uh, this Excel file, now it will be a precast file or the board file. So according to BNBC, so they say pile diameter is 1 meter, pile diameter 1 meter or 0.9 meter. Okay, whatever you like. Say 1 meter pile diameter is very big one actually. Say 0.6, say 0.6 meter. Precast pile 0.6 is rare. Okay, one is rare. You can do it. So it's 0.6 meter. So in BNBC code, if you, uh, if you go to the BNBC, you see the friction, in friction, Fs is 60 maximum for plate epsilon, and or 70 maybe, I forgot. And then this is the tip resistance, that tip or QB, QB, maximum 11,000 for precast pile. Okay, so if factor of safety is 2.5, then you can give it here like this. So factor of safety 2.5, if you see, then the allowable, T or FS. We know FS and FB. Two things we had. FB is the, sorry, or QB. QB maximum. This is the QB 1000. So allowable QB will be, say, factor of safety QB divided by factor of safety. QB divided by factor of safety 2.5. So here, so this one, so this is the area. This is the area. For skin friction is a pi d. Pi d. You see pi d. You see pi d. Skin friction, this pi d. And for this one is for, say, area, cross area, pi d squared by 4. So it's 60 maximum 60, so it's one, if you multiply this one 60 into this, you will get 133, and factor of 2.5, you will get 45.23, allowable one. And then if it is say in 10 bearing, so multiply this one with this, then we'll get these values, divide it to 144, 144 like this is allowable. So these things you have to use for maximum T and maximum F for pi. Okay, and then it is 0.6, 0.6. That's why it is 0.6, and then say your FMC is 30 ampere. The 30 ampere FMC. Usually we use 30 ampere for pi. So EC will be this. There is equation, or you already know this. So we can copy it. Copy. Okay. Copy. Then embedded beam. Say mu. Okay. There is 0.6 meter pi. Pi 0.6 meter. If it doesn't satisfy your load, then you have to increase the diameter. Diameter, because already you know. Okay, so it's identification number is elastic, no need to change. Say it will be underwater. So say the unit weight of concrete is 24 or 23, say 23.5. So minus 10, water table is 10. So because it is underwater, it will be 13.5. Then input method, no need here. Okay, go to mechanical diameter are predefined. The solid circular beam. The solid circular beam, it is this tube, as we have now SPSP, not SP. Then we have the hollow beam. That is the hollow pipe. So then you can go in this way. Okay, it's better to use circular beam. Solid circular beam. The diameter is 0.6. Okay. And then Poisson's ratio that we already, Poisson's not E. E is that is the Young's modulus. So we copied it from Excel to paste here. Then T is skin. So it's multilinear or layer dependent. You can see layer dependent. It will come automatically. Then T max will come automatically, but FX you have to give it. So layer dependent, and maximum you have to give. Maximum is how much? T max that we got it here. For 0.6 is 45.23. Just copy it, then paste here. Then this one maximum. This okay. That is QB or FB, F maximum. So just copy it here. Okay. Okay. Now you have only one file, file 0.0. So now right click it, and then material. What is material? Invert embedded beam, then set material pi 0.5. Or if you don't find there, go here, line 1. You have embedded beam here. Just you see now you have this drop down file 0.6 meter, 0.06 meter. So now file is created. Now we'll apply this settlement at the top. Okay, so the top at this place, at this place will play, apply the settlement, or say displacement, vertical displacement. Then we'll draw the load displacement curve, and from load displacement curve we'll get the bearing capacity. Okay, now again come here, this create line. Now is point load. So point load, this is the point, create point load. This is create point prescribed displacement. So prescribed displacement, click here, then click here. Please 10, 10, 10, 0. If it doesn't match with this point, then just you can change here. You can change here. Now prescribe displacement. The X displacement fixed, Y fixed. Only we apply the prescribe in the Y direction. And which is value? Value is say 0.025. No, 25 milli. 0.025. Okay. 0.025 or if you want to see bit, I mean more, then 0.5 stay. Then from this curve, you can get the 0.25 or it's better 2.5. Okay. Directly the last value will be the allowable settlement. So allowable bearing capacity. So we created this. Now go to mesh. We don't have anything now. Just save it. Save it where? Our case is this place. Okay. So bearing capacity of pile. Okay. Now create mesh. So mesh PDM is okay. And global factor. So mesh is created here. You see, so first, how many nodes now? Is you see 7,141 element and 11635, 623 nodes. So it is 3D. So it has 33,000, 33,000 degree of freedom. So the stiffness matrix will be 33,000 by 33,000 or 34,000 by 34,000. So it's very big. Okay. Now we have to fix one node. Okay. I mean to get the load displacement curve. And that is x is 10. And we apply the load at 10, just top of the file. Y is 10 and z is 0. Then search point. So 10, 10, 10. So node, Node number 4, 10, 10, 0. Okay, it is here now. You see it is here now. Then you have to update here, left side. You have to just click the update. Otherwise, it will not be updated. Now come to the stage construction. Like the previous one, initial stage of the ground formation, or you can write initial phase, no problem. Then it is nothing, point displacement, embedded beam, nothing is there. Then come to next one, the pile construction. Okay, pile construction. Okay. Now, when you do the pile construction, so it is plastic, the same as previous one. And then here the reset the displacement at okay, initial ground there will be displacement, the reset here. It will be automatically like this. Okay. So in this case, just click here left side model explorer, just click the embedded beam. So embedded beam will be selected, already constructed. Next, and then add another step. Okay, that is the apply displacement. Another phase, apply. Already you know this, the same apply displacement. Okay, so here is plastic. Okay, now again during pile construction there will be some settlements. So we have to delete that things. So there the reset the displacement to 0. You see here, reset the displacement 0 because we'll apply the displacement. Okay. Okay now. So all phases are completed. Save it again. Then this is this toolbox, integration DV, and just press it. Then it will be calculated automatically. It will start calculating. File construction finished. Now calculate the third phase. This is so fast. So fast. So it's finished. Save it. Then go to this toolbox again. You see here the view calculation result. You can see the calculation results. Now we need, okay, no, we did not apply the load. Sorry, we did not apply the load. The same thing. So here we have to click the apply load, point displacement, point displacement. That's why it is so fast. Okay, then only this one, you just click here on the left side, then apply displacement. Then again, calculate only now apply displacement, phase will be calculated. You will see load displacement curve here, FZ, now FZ and displacement. Okay. Is stays only 8%, 9%. You can see here, 11, 13% now. Stage, 41% calculated, 54% calculated, and so on, 61% calculated, 3%. Okay, now it's finished. Okay, now come to this starting point. Okay, now you see you have applied 0.025 million. That's the maximum value of U. Now you can see the deformation, or why is that, or this deformation, this one, but you cannot see yet. But you can get it from, left side. You see, you can get it from here. X, say X 10, then Y 0, X 10, then sorry, X 10, Y 10. Then you'll get one section, this section, you see, at the top and at the bottom, you have load. Yeah, you have the stress. Stress. You can even in mesh cluster volume, then you can change it like this. Okay, you can change, just put it here. So this cross section at the top, you see there is settlement, and at the bottom there is file tip. So there will be settlement like this. The maximum settlement is how much? 25. That displacement we apply 25 at the top. Okay, 25. So you can copy it if you declare these things. Then we need this. Load displacement curve. Okay. So now this node number 14, deformation, YZ, UZ, invert this and invert sign because it is negative direction. Then force FZ, invert sign. Then you will get this load displacement curve. Then FZ is left side, and UZ is the left side is vertical axis, and UZ is the horizontal axis. So this is up to 25 milli, 25 milli. So what's the values here? You can get it from here also, or if you can say that only the maximum value, you can say this is the maximum value is 1866. This is FZ, that is kilonewton. So bearing capacity here will be, so you can copy, okay, 1866 kilonewton. So just copy it and draw frame, no need, draw frame legend is okay. And factor 20 or 225, 500, to make a bigger one. And then this, or you can change it here, big, that is node, say bearing capacity, BC, okay, and copy and factor to 50. So now you can paste it here. You see the load displacement curve. So the value here, then that is, so bearing capacity, the allowable bearing capacity corresponding to 25 milli displacement, allowable bearing capacity, you can write it this way, equal to, so you have to calculate for your load case. It's already given. Capacity 18, how much it was? It was, okay, 1866, 1866, 1866 kilonewton. Okay, got the point? Okay, say you want maximum 12 milli. Okay, 12 milli load, and the allowable bearing capacity will be corresponding to 12 milli. Here, in fact, this is 12 milli here, say 12 milli. So from here you will get this value. This value is 1293, this value. So this value you can get it also from this curve, this one. Say 12 milli corresponding to 12 milli, or you can just copy it. This one you can copy into the Excel. Okay, on Excel to copy it. Okay, this is your UX, user, this app there. So corresponding 12 milli, the maximum is 13,000. Let's make it number, then this number, decimal 2, you can get the values. Oh, here that decimal 4 you need at least. Okay. So 12.04 milli, so it is 1279 kilonewton, your bearing capacity. Okay. So in fact, in IS code, I mean, they consider this is displacement, and they consider just that, I mean, bearing capacity of a pile corresponding to 12 milli as I mean the settlement. So it's 12 milli settlement, so it's 1297. Okay. So in this way you can write like this. Understood. So this is the vertical okay, this is a bearing capacity, axial bearing capacity, and you also need the lateral load bearing capacity, lateral bearing capacity. So you have to do a hand calculation. You have to use here also. Just save it, then close, save it. Huh? So this is ultimate bearing capacity of pipe. Now you need lateral bearing capacity. So you can just use this one. File save as. I already saved it. Save the project. The bearing capacity, lateral bearing capacity, huh? Or lateral load capacity, lateral load capacity. The same thing you can use. Out of file. So now come here, the same soil, the same thing. Okay, now only this line load, that is, I mean, it's sorry, point load, the point displacement, that is point displacement, is this one the point displacement now. Or you better you come here, point displacement here. So point displacement. So now we can change it, the horizontal direction. So it is in the x direction. So x is prescribed, y is fixed, this is prescribed. Okay, this is fixed, z is fixed. Now it is say you apply, I mean 12 milli, maximum 12 milli we use, as we learned in sorry, foundation engineering, 12 milli. Okay, corresponding 12 milli, I mean the lateral load is the allowable lateral load capacity. Okay, other things remain same, so you have to, I mean, generate the mesh again. So generate the mesh. You have pile, everything is there. Okay, it's already generated. You see, already generated. Now you have to fix one. Fix the node. Again, you have to fix this node because you see there is no node. I mean, fixed here, assigned here. So it is at 10, sorry, 10 meter, 10 meter and 0. Search closest. It is the same 10. Okay. Then you have to, in the left side, you have update. So update it. Okay, it's updated. Now come the stress construction. Okay, now initial phase is there. There is nothing in embedded beam. Then file construction, embedded beam is there. No point load is there now. So everything is there. So save it, then calculate it. Calculate, then you will get the load displacement curve. Okay, you will get the load displacement is finished. Now we'll save it and we'll go to the result option. So this output file terms, you see the maximum value is 0.12, it's 12 milli, for 12 milli. Okay, so you can see also the deformation, deformation of this one. So now is y-x, y-x or you can see. So you see here at the top. Okay, if you take this, I mean section, then this section, if you take it, then you can see the, I mean, the distribution of lateral displacement. Now come to the load displacement curve. Now new, as it is new file, project, node 14, stress, total is now is ux, ux, and it is positive, no need invert. Then force, it is positive, sorry, it is fx, fx, select fx. Now it is okay. Okay. Now you see this is your load displacement curve. It is in the elastic range. So the value here, so you can copy it in your Word file, and you can change it in the lateral load capacity. So you can write it here, lateral load capacity, lateral load capacity, no lateral load, or okay, lateral load versus displacement. Okay. Apply, then And the value is here. You can get it. The value 12 meter is 554. 554. So lateral load capacity is 554. Copy, draw, say 250, then paste it in your folder. There is axial capacity, allowable axial bearing capacity. Bearing capacity. Bearing capacity means axial load capacity. Axial. The same. Setting. Now it will be lateral load capacity. This one. The lateral load capacity. Lateral load capacity equal to how much it was? Forgot. 542. 542 kilonewton. Okay. In this way, you can get the lateral load capacity and then bearing axial load capacity. Understood? Okay. Now save it, close, save it, close. Okay. Now coming to mat foundation. Not even file, whatever you like. File foundation. Now bearing capacity, from calculation and from here. So if you have 4 layers of soil, then you have to make 4 layers. If you have 3 layers of soil, you have to make 3 layers of soil and put the pile here and so on. Okay. Now we'll go to say now what we'll draw. We'll draw. Okay. Now we'll draw say our pile. Say the sorry. Okay. Say your plan. Okay. Say your plan is like this. Building plan. You already know. You know this area. So you have column here. So you have column here, and so on. Okay. A column. Okay, plan view. Okay. So in one column, say the mid one. The mid one in one column. So now you need say 4 pipes or 6 pipes. Say 4 pipes. Okay, or 6 pipes. So now we'll work on it. Design load you already know. Design load. So design load you already know. So say the total area. Just I will give you only one, then you calculate. You put later on. They will make one. This is your ground. Say you have 2 layers that I already explained. Okay, and you have 4 5. 4 5. We'll work on that. In section view. Say, oh, I see it is here. Okay. The inspection view say you have 2 pipes like this. So this is 20 meters. Okay. And say this pile cap you used say 0.8. 0.800 milli. 800 milli or 0.8 meter pile cap. So I will start again one project. Okay. Now Plaxis 3D. Again Plaxis 3D को कैसे प्रॉब्लम देखा नहीं এটা না তো 3D connect really 3D input. Okay, I have both version. Today only 44 participants, 43 participants. Okay, record is going on, yes, recording. Now say pile cap, pile cap, a pile foundation, the pile foundation. Okay, model, full 10. Say now your area, whatever your area is, you have to increase the area. At least you need 10 meters from each side. Okay, so this is your, area, but you have to take say 10 meter, 10 meter extra. Okay, for avoiding boundary condition, or 20 meter extra in both sides. Say 10 meter, this is 10 meter, and so on. 10 meter, 10 meter. Okay, and both sides. Next and y direction. Say you'd so, but we'll take later. Here. Less uh, smaller size, because it will not. It will take time. If we take. Bigger size. Okay. So say for our case, we have a 20 meter, a 20 or 15 meter. Okay, 15. Okay, 20 meter. 15 meter, because it will take time otherwise. Okay, 20 meter, and then this one is say 4 meter. This one is say 30 meter. 30, sorry, 24 meter. 26 meter. In total, we have 30 meter like the previous one. Okay. I would say 20 meter. 20 meter is good, because previously we did also 20 meter. Okay, 20 meter. Now, they pile once this size is say 3 meter, 3 meter by 3 meter. 3 meter. No, you don't need. Say your pile, here's the pile is here, and column is here, and say 2.5 meter. 2.5 meter. Then this is 2.5 meter. Then center to center is say it is 0.6. 0.6 into 3 is how much? 1.8. So 1.8. So it will be at the center to center 1.8. 1.8 meter. Okay, 1.8 meter. So you have to draw it first, then go for the Plaxis analysis. Okay, so we have 20 meter again. We are using 20 meter. Why? Sorry, maximum 20 meter, 0 to 20 meter. Okay, okay. Now, soil. Then first you have to draw a borehole. Create borehole. So it's repetition. Then it will be easy for you. So here state water table at top. So 0, 0. You have water table at top. Okay. Then add a layer, say -4 meter clay layer. Then we have -30. Add another layer, that is -30. Okay. Okay. So now you have to create again the same thing, that say molecular model. So as we have already created, so we can copy it. You can keep it in the memory of the Plaxis. So we cannot open two files together. That's why we save it first. Here we save. This enter. Okay, we save it. Save here. File foundation. Okay, the same place. File foundation, and close it, and come to the previous file, PDF file, whatever you like. It's lateral load also, no problem. Then click it. Okay. Now open the material state. So material state, you have these two. You see, just keep these two. Just control, and then keep here. Molecular model clay 1, stand 1. Okay. You have not plate element, you have beam element. Okay. 60 milli, then keep it there. Oh, no, no, not here. Sorry. File. Oh, yes. Embedded beam. Okay. File 0.6. Okay. So, any other material was there? No, nothing. Okay. Now again, open file foundation. If you have any question, you can ask. If you don't understand, then you can ask. Now, you see there is no material assigned here. So, now open here to all files. Now we have molecular model. Actually, we'll use just bring it here. Oh, all. Sorry. All. All. Delete. Yeah. Okay. So, now we have two models. Play model. Oh, no, HSK play. No, this is not. Then delete. This thing. You need this. You need this. Okay. Then embedded beam, you need 0.6. Okay. And yeah, you can take the raft. I have raft here. You can take it from there, but you can create it. Okay, raft in plate element. And we created one. First the raft or pile cap will create from there. Okay. Now, if you click here at the top, you will see the first layer. That is, there is nothing metal set. So now it is clay layer. Then bottom, you select there, then it is sand layer. And all parameters as already okay, already, you defined it, then it is molecular model, untrained behavior. So you can save your time in this way. Okay. So the material parameter already set. Now what we need use file, 4 files and file cap. Okay. So first create file. File. So how can we create? Go to the structure menu. Then here create line as it is previous one. And here, okay. So it will be, the file will be, and come here again. So what's the location of the file? So it is 20 meter. So this 20 meter data center. Okay. I can use another one. Okay. There, in 2D you can see. Okay. This is your column. Okay, center. So we have pile here, pile here, pile here, pile here. Okay, a bit bigger. I'm showing. So this is 0, 0, 0, 0. So this point, this center point is 10, 10. It was 20 meter. It was 20 meter. So you have to keep it like this. You have to use this coordinate system. So center is 10, 10. This center 10, 10. Okay. So it is 2.5 meter, 2.5 meter, 2.5 meter. Okay. 2.5 meter. And it was 1.8. Center to center, 1.8 meter. This is 10. This is 0.9. 0.9. This is 0.9 from here. So 0.9 means this will be in x-axis. X-axis it will be 0.9. 10 minus 0.9. So 9.1. 9.1. And y-axis also 0.9. 0.9. So 9.1. Okay, 9.1 by 9.1. Okay. In first one. Okay, now come to the, come to this one. Just a minute. created. So top is 9.1, X is 9.1, Y is 9.1, the first one, 9.1. Then this Y is also 9.1. Top is Z equals 0, X is 9.1, and Y is 9.1, and Z is minus 20 meter, Z 20 meter pi. Okay. So this one you created, this line. And now create file element. The same is same like this. This line create file embedded beam. As you know, embedded beam is been created. Okay. You see material. So material is 0.6 meter. That we already, got it from our previous file. Okay. Now you see you once this. Now you go to array to make array. Other places array. So it is 1.8 meter interval. Array in x direction you have two files. So it is 1.8. 1.8 meter interval. So it is, yeah, okay. It will be 1.8 meter interval, but it will be, yes, 1.8. Okay. Now in y direction. In y direction, so go there, y direction is 2. So again 1.8. Then other file will be created. Now you select this one, other one, and then go to the array. This is the array. Okay, array. So it is y direction. So it is 1.8 interval. Okay. We have created the file here. Create the file. Okay. Now you have to create the, file cap. File cap. So you have to go here. Previously it was line in 2D, but here create surface. This one. Create surface. Come here. So because it is grid line, so it will not come here. It's 1.2. So right side, come this, then this. Now you can change here. So x will be how much? 2.5. So 1.25. So 10 minus 1.25, 8.75. Understood? You have to make everything. This means this first point, red one. This first point is 8.75. And this last point will be 11.5. 11.5 because it's 2.5. 11.5 x-axis, and y-axis also 8.75, but here y-axis will be 8.75. 75. So this one will be x-axis 11.25 and y-axis also 11.25. This one x-axis 8.75, but y-axis 11.25. Okay, like this. So these things you can adjust there. Okay. Okay. So 8.75, y is 8.75, z is 0. Okay. We can make it at top. Then this is 0.2, this is 11.25, and x is 8. Y is 8.75, z is 0. Then it is 11.25. So y is also 11.25, 0. Then this is 8.75. This is 11.25. Okay. You see that plane state is okay. So it's okay here. Now your file cap has been created, but it is surface. Now you have to create a plate. Plate. Right click, create plate. Okay. Plate, but it doesn't have any material, but we have raft, but that raft is different one. So go here, the file cap, plate element, edit. This is file cap. File cap. uh, or we can cancel. We can copy because we can use this one in the next. Okay, mat. Yes, we can change the mat. So edit, then copy. You can copy it. Copy, wrap. So it is copy. Say file cap. File cap. Say 800 milli file cap. Okay, 800 milli file cap. So it is what you need. You need gamma. Say gamma is say 1 or anything. Say here gamma is not given. So it's above the water table. So concrete unit weight. So it's 23.5. So it is minus 10, 13.3, 13.5. Mechanical EI. It was 30.16. Say 40 megapascal in limit. Now come to Excel. File cap. Say EC. Say 40. Also footing also no problem here also the same thing. Say 23.5 is your unit weight, and then it's 40 MPa. Okay, 40 MPa. So 28.786. Copy it, paste here. Is isotropic value. Okay, isotropic, then it will automatically. And then percentage 0.1. D is 2.8 meter. Thickness 0.18 meter. Okay, so it's okay. Okay, now you can assign file cap. Okay, so our model is created. Okay, now we need to add, design load. I don't know how much you got it. Say you design load got say how much I forgot. Say 4 mega Newton. 4 mega Newton. Okay, and so on, or say at 1 mega Newton, 10,000 kilonewtons. Say, or say one. It was how much? 1,000. The bearing capacity for 12 milli. Okay, the bearing capacity. So for 12 milli, it was maybe 1200. 1200. Say 5,000. Or 4,000. Say 4,000 kilonewton your design load. That is coming from your calculation. From structure. Design load is if that column say 4,000 kilonewton. So come here. Now add load. This point load. So here this point load, which is at the center, is 10 10. 10 10. If it is not, then you can change point load. So you can put it here. It has fx, fy, fz. Fz is 4,000. 4,000 kilonewton. You got it. And then a moment. You can apply moment. Moment about x-axis, moment about y-axis, moment about z-axis. You can add it here. Okay. Of course, you will have unit calculation. Fx also you will have because you have to do lateral load. You can get lateral load. Okay, and so on. So you can put it there. Say lateral load is say 40. Say in expression 40, 400. Not 400. Say 100. Say this is Fy is say 100 and so on. Say moment in x direction. Any value you can give. Like this. Okay. So finish. Then create mesh, medium or finer. So it is 7,735 element. Sorry, no element and node is 12,000 something. So now say we want a load displacement curve at some places. I think no need actually. We don't need, in fact. Okay, no need. Cancel it. Okay. Okay, because we don't need any load displacement curve. Come here. The initial phase, if you double click this K0 procedure as previous one, we know that. Then add construction pile and pile. Construction pile first. Construction Here, come here, construction, file first, file. Then this is the one, and then you see this reset the displacement. Reset the displacement is very important. Constant file. Okay. So here, what you will do, you will use the file only. You see, you have 4 embedded beam. 1, 2. If you go to the Model Explorer, you see embedded beam 1, 2, 3. This is all. Or you can click here. You can get all together. Okay. It is inside the file. So inside the soil. Inside the soil. Or you can see here. Not here. In geometry, if you see now it started. Okay. Say it is gray. If you click it, it become active now. Active. Okay. And then and also you next you construct mat or pile cap. Say pile cap construction. Pile cap. Pile cap together also. Pile cap construction or installation. Installation. Again, you reset this one. Reset is 0. File cap construction. You reset the displacement 0. Okay. Now finish. Then in this stage, you have to use this only. There is one point. Sorry, not point. Plate. What is the plate? Okay, embedded beam. Okay, this plate. You have only one plate. That is pile lab. Just click it. You will see it will active. Now this plate is activated. Now next one, apply the design load. Apply load. Here change it. Apply load. So it is after the pile cap construction installation. Now reset the 0. Okay, reset 0. All displacement is 0. Okay, so your process or procedure has been finished. Now start calculation. Calculation. Select nodes and stress point. No need. We need ignore this feedback. Then it will start calculating the steps. You see, this is not very, very difficult. You can get it by 1 hour or maximum 3 hours you need to learn this Plaxis. Okay, save it now. Go to the result. Okay, now result is here. Okay, now what you need? You need, okay, you need first deformation. Okay, or you need a pile load, pile moment, pile shear force, and so on. And also you need a pile cap, shear force, and bending moment like this. So if you select here left toolbox, if you see there is this one. Select structure. Click structure, select it. If you select, okay, if you select like this, you have plate and embankment both. Okay, and embedded beam. The beam first is select, then select. Okay. And come here, I don't know why. Okay. Embedded beam and select, or you can say this is your things. You can, then one, I can F4. Okay. So this is again why it's not working. Okay. Only one beam is one file is coming here, or all files. You can go to that one. Go again, or not here. The window, the previous window. Okay. Okay. Previous window. Shift and then all pipe. Yes. shift, I mean press shift and double click. So you'll see you don't need that boundary, cluster boundary, no need. So now you have pi, pi. Now you see here that YZ, that is displacement in vertical direction, total displacement in vertical direction. So total displacement in vertical direction is 10 to the power minus 6. This one, very small for your case, very small. Okay, so you have to, keep in mind it must be less than 25 milli. Very small. Here is even less than 1 milli. Okay, so this is your displacement. Now we need the forces. The axial force. So axial force is 25 kilonewton. Oh, I see. I applied very small value, maybe only 25 kilonewton cap, 22 kilonewton. You see, we have to change there. Only 22 kilonewton. Now come to this is the axial force. Then here force is the shear force. Shear force. Okay, only one. Then shear force here. Here, Q3 very small value. So it's better we close it and again we put the values. Oh no, we did not apply the load. You see, we did apply the load. You see, point load is there. No, not delay connected. Yes. Now point load is there. Point load. So always we make mistake. So it's point load now in the apply load section. Now calculate only this thing. Only this one calculate. That's why it's very small. And it was very fast. Now it's only 44%. 73%. 86%. 95%. Okay, I finished. Now you can see the sometimes. Previously it was mistaken. Okay. Okay. Now you see 10 million. Okay. Okay. Total displacement deformation is 10 milli, 10.95 million. Total displacement. You can see the sections even, sections, mid sections, any sections you can see at the, from this, left side toolbox, you can cut at any the sections. Now we don't need this. We need only this one. Okay. Okay. Embedded beam. Select. Oh no. Here. Then again. Okay. One by one you can do it. Okay. Now beam is here. Column. Pile is here. Okay. So this is your pile. So maximum seven was 10.50, which means an allowable limit. Allowable limit. Now you can see the axial force. So axial force is 800. 800 maximum axial force minus 800. Okay. Normal and axial force. So your allowable bearing capacity was that around for 12 milli, it was 1200. So it's okay now. And then shear force. Okay. Get it. So you copy it. Always copy it and paste here. Paste here always. You do it. And for your case, for every file, so you can make report. Like this. We need shear force. Okay, we need shear force. So this is the shear force. The maximum is coming here because we are not applying the load at, very low, load. We don't know, arbitrary we put it here. Say here, this one. or you take one, select one, the maximum one is here. So you double click it, one, you can make it bigger even. You can just click here, click, then scaling. You can manually scaling it, it's 0.1, say it is 10 times, 10 times scaling. Okay, so you see this is your, shear force diagram. Okay, shear force, the maximum shear force, you will get it from here, so 66.9, 66 kilonewton. Okay, so in one pile, 66 kilonewton. Then moment, how much moment? So you go to the window, previous window. Okay, previous one window, the moment. We don't know which one is bigger. This is almost nil. M2 36 maximum and M3 32. 32. So here say you click one, this one you click one and make it bigger. Mesh. Okay. Okay. Double click, right click this one, scale, manual scale, say 10 times, not just say 0.1, 5 times. You are making 5 times. So this is your, this is 32, 32. Okay. And then paste here, paste here. Okay. So this is the moment, moment 3 and bending moment, so on. Get it? Okay. Now, once you get that, you can design how much, from there, you can design the, what, reinforcement, reinforcement, how much you need, then you can, select from there, choose from there. Now, raft, coming to the raft or pile cap. Okay, then window again, go to the second one, maybe, no, go to the first one. Okay, this is your raft. So select this double click. Now you have raft only or pile cap only. So cluster, border cluster. So this is your raft or pile cap. So in this pile cap, okay, you will get these values. UX, Z and so on. Or you can get, all information from the table. Okay. So table, how much the maximum, you will get it, how much, the UX, this is displacement, sorry. Go to the previous one, then force, say Q1, how much is 50.3222, then Q12 is 50.32, Q13, 2170, okay, shear force, 2170 shear force, maybe this is the highest one. Copy it, okay, then paste somewhere here. So 2170, the highest one in this way, and then moment, moment is 1011, 1011. You have to check 1010. Maybe this is the highest one, 1011. M22, this is the 10, sorry, M11, 1011. So copy it, okay. Now you know your, moment, you know your shear force and everything from the, from the Plaxis analysis, okay. Now from Plaxis analysis, you know it. Now you need to calculate the shear force. Already you know the shear force maximum one, minimum one, bending moment and so on. So I have one. Then you can get the reinforcement, and thickness is okay or not. You can check. Say concrete, 40 kPa for 40 MPa, and then steel, say 60 grade, say 60 grade or 72 grade or 60 grade, say 72 grade. You'll use it, and then your moment is how much? This is shear force and then moment. Say your moment was, from there you'll get the moment, say 1011, 1011. So it is 1 0 1 0, sorry, no, moment is 1 0 1 1 1 0 1 is moment, then so not here. Shear force was 2164 or 2170, not here. File 2170, and you used 8. So you see, you need 16 millirod, 53 interval. Okay, center to center. So it's, I think it's 16 milli. You have to increase the diameter, say 20 milli, 82, because the spacing at least 40, 100 milli spacing you need, or what, or 5 inch. Okay, say 25, 25 milli rod you have to give. So it's 0.8. The thickness is okay, design is okay, thickness is okay. So 0.8. Phase 1, if you give it 1 meter, then 165 repair. So 0.1, 0.8 is okay. So your rod spacing will be 25 milli rod, 126 millimeter, or 125 milli, 5 inch, interval. Okay, center to center. In this way, you can design the pile cap. Okay, understood? So now coming to mat, and very similar to this one. Now delete this. Coming to mat, now you will not have any mesh. Pile. Okay, only mat. Okay, so it will be say 2 meter below the foundation. Okay, below the soil. So mat foundation. It will take more than 10 minutes. Okay, we'll use the same. Now save it. Okay, save the project, mat foundation. So you'll try with mat, because mat is very stable foundation. First you try with mat, then if there is huge settlement, then go to the pile foundation. Okay, the mat, and now it's huge mat. Okay, so come here. You don't need this file. Okay, we'll delete this file. Okay, we can select it, then delete, select it, delete, select it, delete, select it, delete, or you can select from here also. So here there are some points, so we have to delete this thing. You select it, point, these 4 points you have to select, delete. Also here, all points you have to delete. Okay. Okay, accept the, okay, wrapped. Sorry, better use this. Okay, now you don't have any point, only you have wrapped. Okay, so wrapped will be at 2 meters. So what you have to do, if you go to the wrapped, you always think it will be say under 2 meter or 3 meters like this, or basement if you have. So here you have the foundation. So maybe here the ground level. So mat will be here, mat foundation will be here. So say 3 meter. You consider 3 meter, 3 meter. You consider. So say what we used here now. Clear 4 meter, and then 26 meter is 10 layer you have. So what you have to do, so you have to use this clay layer, this layer. So it is at 3 meters, then now it is 1 meter layer, and below 1 meter. So you cut it, or what you do, initial mesh will be smaller, size will be smaller. Okay. So you go there, go to the soil, change here, change soil. Okay, soil, modify the soil layer. So clay, it is -1. Now the top layer you don't need. Now it is -1 to say -27. 27. Immediately we cut it. So okay. So it is okay. Or you can make it more smaller one even. because now we don't have any pile. I mean, you can decrease the depth. You can decrease the depth and it will be very fast. The depth up to minus 20 meter we are considering. So one clay layer is 1 meter, and then sand layer 19 meter. Okay. Accordingly, I mean, you have to change your parameter. So now say mat come here. Say mat is your total area say 10 meter by 10 meter. So double click it. So 10 meter. So it's in total 12 meters. So it's 5. Then coming to 5. Sorry, 15. Then this will be your 5 meter. This is 15 meter. This is okay. This is 5. Sorry, this is 5. So this is 5 also. This is 15 meter by 15 meter. So 10 meter by 10 meter. Your I mean area. So it is 5. So it is 5 and then 15. Okay. So this is your mat foundation. So this mat foundation finished. Now say mat foundation thickness will be. Now it is pile cap. Pile cap given. Now coming to the raft. Raft. A plate element you have raft. So it is given. Say mat is 13.5. Our table is there. Mechanical. It is 2 meters given. Say the mat is a 1 meter mat. You are placing in 1 meter mat. And then EI that you will get it from here. Putting on mat is 40 MPSA, so 28.8 at this kilopascal. Put it there is isotropic condition. So it is like this is 0.15. Okay. Now you apply the load at all points. Apply load at all points. Say you have point load this point and okay this point that is okay. I'll make it first. So this point select it. So 0 at any point. I don't know what's the point. So you have load here. Say load here. Say 4,000. 40,000. That direction, and you have moment and so on. Okay. You have moment. You put it here, and say we'll make it array in both directions, xy directions plane. So it is say 3 by 3. Then axis say 2 meter interval. So 1.5 2 meter interval, but because it is smaller, 2.5 meter or 3 meter interval. 3 meter, and y is also 3 meter. That's why. So it's created. Oh no, it's 3. Stay, Yep. There's again. Dash xy direction. 2D in xy plane. Then it is 3. The 3 meter interval. Then it is 3. Sorry, x 3 meter interval. Okay. So it is your foundation load, column load. Okay. So now make mesh. Okay. Yes. Now come here, stress construction. You don't have any pile, delete it. Delete the pile. Yes, delete. And now pile cap. It is not pile cap. It is wrapped. Wrapped installation. Wrap. Wrap. Oh, previously we did not change maybe. Structure. Did we change this one? No, it is pile cap. Here is this the pile cap. So it is wrapped. Okay. Now you don't need to change the mesh. Okay. So it is now apply load. Now you have point load. How many point loads? You have 9 point loads and 9 columns. So there are 9 point load. The total you in the apply load. Okay. Then click calculation. You get the calculation, and you will the same way you can design, or you can check the thickness whether it is okay or not. Understood? Calculation is running. Okay, now finished. Then come here, see your data, check deformation first because this is very primary important. Say you have 136 milli. You see the value is 136 milli. So it's not allowed limit. Okay, the allowed limit for mat in clay maximum 50 milli. Okay, so you have to go for pile foundation. Okay, if it is less than this, then you can keep it. Okay, so now, okay, or you can see the mat. Huh? Mat. Okay. The deformation is you see 31, 36. And from there you will get all forces, shear stress, shear stress in all directions. The 2669, you did 2469. Okay, 2469, maximum one maybe. So in thickness, you can check, not thickness, yes, thickness, where is thickness? Yes, 2 for shear force is okay, I think. And then bending moment, when at 1527, there will be other things also. We don't actually, we get the arbitrary values. So you put there and then you can get the reinforcement in both directions. Okay, understood? You can fix the thickness. You first, place one thickness in the Plaxis, and from there you get the values, and then later from a moment and shear force, you can fix the thickness and then reinforcement of the rack. Okay, now you can give your attendance in the chat box. If you have any question, then you can ask. So I'll give this record to all of you so that you can do practice and you can finish your homework. If you need this file also, this practice file, then I can give you, but also Excel file. If you need that, I can give only the parameter, not this. Reinforcement I not give because you have to calculate. You already know, how to calculate this thing. Only I'll give this parameter one, this parameter, because you need this. Precast pile or board pile, whatever. Precast pile maximum 6 milli, 6 milli. In our case, in dormitory, boys dormitory in IUT, we use precast pile of 400 by 400 milli. Okay, that was rectangular. It is circular, I guess. Okay, I can give you this one. You can save it. So I can stop now. Whether you finished your attendance or you just message that. Sorry, chat box will be message. 37 out of 44, 45, 38, 89. Okay, okay then. 41. Okay. So I will stop sharing this one. Now I'll end this one. Stop recording.